The world of plants is exceptionally diverse, so when it comes to deciding on materials, artists need an intuitive way to both find and select them. This challenge is something I've already encountered in the last video when selecting shapes for each component of a mushroom. While I initially settled on a drop-down checklist with image tooltips, this solution is hardly perfect. A far better approach is through a dedicated asset browser, and what better example to take inspiration from than Quixel Megascans. With tens of thousands of materials and 3D models in its archive, Megascans has numerous filtering tools available to help artists narrow down their search, and for BrightLife, I'm going to implement a similar solution. Building up the interface for the asset browser is a fairly straightforward process. Where things get a bit trickier is the creation of individual items. Using some clever tricks with HTML, creating the UI design of each item is relatively simple. However, additional information is needed to categorize and filter them correctly. Therefore, I created two custom metadata formats, one for meshes and the other for materials. These files use a similar structure to BrightLife project files, allowing me to reuse the existing loading system to save time. Upon launch, BrightLife will locate and process all the meta files it finds for shapes and materials, creating an asset browser item for each one. Then, a filtering function uses the metadata of each item to only return the relevant entries instantly. With the asset browser done and dusted, artists need to be able to launch it from within the BrightLife interface. For shape selection, I created a new UI editor for the property grid system to replace the drop-down checklist I started in the last video. Once again, designing a property grid editor is a bit of a faff, but after a while, it slowly comes together. The existing values for shape selection is also passed on to the asset browser. That way, it can pre-select the shapes that are already being used. The introduction of metadata files also removes the need to preload the plant component meshes upon startup. Now, BrightLife will only load the assets which are needed. And using Bright Engine's dynamic memory management system, shapes that are no longer being used are removed from memory. The end result is faster loading times and reduced RAM consumption. To launch the asset browser from the BrightLife editor, I quickly populated the material tab that has been empty until now. The layout is similar to the shape tab, where the artist can adjust the individual parameters used during the geometry generation of plants. Artists can select multiple materials, which will then be randomly assigned to the target component. The materials themselves are split into two primary classes. The standard material class contains a pointer to the shaders and textures stored inside the Bright Engine Resource Manager. The smart material class contains a pointer to the standard material being used, along with the additional settings that can be adjusted by the artist inside of the material tab of BrightLife. In addition, I created another 3 auxiliary classes to improve organization and access to these materials throughout the codebase. The Plant Shape Library and Plant Material Library classes store a list of pointers to the metadata for meshes and materials respectively, as well as handle the loading of the connected assets. While this does add an extra step, it makes it easier to ensure there is no data duplication in memory. The third and final supplementary class is the Smart Material Manager. As the name suggests, it's responsible for the creation and management of new smart materials using the information provided by the Plant Material Library. The Smart Material Manager also contains a list of pointers to all of the smart materials currently in use. It also houses the default smart material that's automatically applied to plant components that haven't been assigned a specific material by the artist. While the introduction of these materials wasn't too problematic, they revealed a serious problem relating to loading speed. The materials currently available inside the BrightLife ecosystem are all 4K resolution and saved as PNGs. This format provided the most optimum compression, resulting in a relatively small file size on the hard drive. However, the decision to use PNGs didn't take into consideration a critical factor: mipmaps. Mipmaps are used across almost all textures within a game. They are an optimized sequence of images generated from an original texture, with each mip halving in resolution. Game engines use mipmaps to dynamically change the resolution of textures in real time. Assets far away from the camera likely don't need full detail, therefore a lower level mipmap is used to improve rendering speeds. As such, they need to be generated whenever the texture is loaded into memory. Generating mipmaps isn't difficult, but it's time consuming. For a single 4K resolution material that has 7 different PBR textures, the generation of mipmaps took close to 30 seconds, and since plant projects are likely to use a large number of materials, the loading times were horrendous. This is where the Direct Draw Surface format comes to the rescue. Despite being released over 25 years ago, the format and variants of it continue to operate behind the scenes of most game engines, including Unity and Unreal Engine. How this format works in detail is a bit complicated, but in the case of BrightLife, the biggest advantage is being able to save pre-generated mipmaps inside the texture files themselves. This does increase the overall file size of textures on the hard drive, but it also reduces the loading times per material from half a minute to less than a second. Performance was further improved by saving the PBR textures as channel-packed images. Roughness, ambient occlusion, metallic, and height maps are all grayscale textures that can be packed into the red, green, blue, and alpha channels of a single image. This reduced the number of files needed to be stored per material, resulting in fewer I/O calls by the CPU and fewer texture binds by the GPU, improving both the loading and render speeds respectively. With material selection done and dusted, it's time to build a fully functional PBR shader. Up until now, BrightLife has been using a basic color shader to display the geometry within the viewport. Needless to say, a PBR shader is a bit more complicated, and it requires a lot of additional environmental data that I previously described in the second devlog video of this series. There are numerous approaches to take, each with its own advantages and disadvantages, but just like Bright Engine, BrightLife will use the roughness metallic workflow rather than the specular gloss. It's a bit more intuitive, and with all color values captured in an albedo map, there are more grayscale textures resulting in more channel packing opportunities. Regardless, artists will still be able to export their selected materials to be compatible with either workflow. For those interested in the mathematics of physically based rendering, the methods I've chosen are Cook-Torrance approximation for BRDF map computation, Trowbridge-Wrights for the normal distribution function, Fresnel-Schlick for reflectivity function, and Smith-Schlick-Beckman's approximation for the geometry function. These were selected based on the research of Brian Karras and Sebastien Lagarde, who worked on Unreal Engine 4 and Frostbite 3 respectively. Luckily, all these complicated formulas are already built into my Bright Engine SDK, so I don't need to deal with working out the mathematics again. However, there are still some further adjustments needed to improve render quality. Rendering in a high dynamic range frame buffer allows for a wider brightness spectrum to be displayed on screen, but to benefit from this visual improvement, color values need to be converted from sRGB into linear space. A cheap and easy trick to achieve this is by using a gamma 2.2 curve. Unfortunately, it's ultimately flawed due to being highly inaccurate for dark values. In fact, it's mathematically incapable of producing a true black. Therefore, despite the added performance cost, converting to and from linear space should be done accurately. Another necessary adjustment is specular anti-aliasing. When working with low roughness values, especially on curved surfaces, the formation of firefly artifacts is quite likely. These create jagged edges within the reflective surfaces that can hurt the quality of the final rendered result, despite being mathematically correct. To solve this, extreme roughness values are adjusted based on the normal angle between a surface and the camera. The end result isn't technically physically accurate, however it produces a much nicer image. To finish off surface rendering, a solution for displaying height maps is needed, and for the time being, I've decided to implement a parallax occlusion effect. Similar to a normal map, parallax occlusion gives the illusion of depth on flat surfaces. This is a form of optical illusion where the UV coordinates used to sample a texture are adjusted based on the angle between a surface and the camera. It's generally quite a cheap calculation in terms of performance. Unfortunately, it also has its limitations, creating strange artifacts at certain angles or if the strength is too high. While artists can manipulate the strength of height maps, a better solution may be needed. Tessellation is a bit complicated, but in oversimplified terms, it's the equivalent of subdividing a surface and repositioning the vertices along their normal axis using data inside of a height map to create geometric depth. Due to its high performance cost, it's often used sparingly in video games, but for the purposes of rendering a preview inside of BrightLife, the longer render time is insignificant, especially since it's far more accurate than parallax occlusion with none of the unwanted artifacts. Just like how artists can control the strength of a height map, the other PBR textures can also be modified. Various settings are in place to adjust each material to create a wider range of unique results. But in addition to material rendering, I added a basic directional light source. Settings for the directional lights, such as strength and color, can be adjusted, and by holding down the shift key while left-clicking and dragging, the angle can also be changed. It's a fairly basic setup, but it allows artists to recreate a closer replication of the lighting environment within their games to generate a more accurate preview. While the lighting is also based on approximated simulations of physical light, the final render result still looks a bit like clay. The cause of this is the lack of subsurface scattering. Every type of surface absorbs and scatters a certain level of light. In video games, having this detail is essential for photorealistic skin, but the same applies to plants, especially leaves. For artists planning to make phosphorescent plants, such as glow-in-the-dark mushrooms, adding a physically based bloom effect will take the rendered preview to the next level. Therefore, just like tessellation, physically based subsurface scattering and bloom will be introduced later down the line. Until now, each node contained a list of generated components which were looped through and drawn one by one. But now that materials have entered the picture, this rendering architecture is no longer viable. It's perfectly possible to continue looping through each of these components and sending the necessary textures to the GPU for each one. However, this will result in a significant number of texture bind operations. Therefore, instead of storing generated components in the node class, they're now stored inside the smart materials. During each render pass, BrightLife loops through each smart material that has components assigned to it. It binds the textures of this material and then draws the components in the list. This means that textures for each material are only bound once per frame instead of once per component, a drastically faster way to draw meshes on screen. Another 4 texture binds per frame have been eliminated by standardizing the texture slots. As a quick crash course, only a certain number of textures can be bound for rendering at any one time. By reserving the first 4 slots for the environment, pre-filter, radiance map, as well as the BDRF lookup table, these textures only need to be bound once outside of the render loop. These performance optimizations can even be taken further through mesh instancing. Instead of drawing each component within each material one by one, the model matrix for each component can be sent in one giant batch. The GPU will then draw the same component mesh multiple times in multiple locations based on these model matrices. This reduces the number of mesh draw calls down to 1 per material, rather than 1 per component. With the completion of the asset browser and the introduction of materials, BrightLife is getting quite close to reaching a minimum viable product. LODs and wind simulation are next on the to-do list, but even once BrightLife becomes feature complete, a lot of work is still going to be needed to extend the number of plants it can generate, as well as expand the material library. The small collection of stylized materials features in this devlog was kindly donated by Alex over at Lowly Polystore. He's an expert at crafting high-quality game-ready assets and has thousands of stylized materials available to buy right now. So for those working on a stylized project, you can use the following promo code to get yourself a nice discount. There's a link in the description below. While artists will be able to import their custom shapes and materials, having a diversified and extensive library of assets is essential. Unfortunately, this doesn't come cheap. Photo scanning materials requires a lot of fancy equipment, and creating stylized ones is a time-consuming process. Therefore, to help fund this project, I've decided to launch a Patreon page. You can support from just $1 a month. Those that do will be able to download BrightLife in its current state right now. As always, let me know your thoughts about the progress of this project in the comments below, and don't forget to subscribe to secure your free copy of BrightLife once it's finished. Thank you for watching, and I'll see you in the next one.